Welcome everybody. We're back in the Bayesian machine learning and information processing class. This is the lecture on dynamic models. It's a short lecture, and that's by design. I mean, that's on purpose, because normally, dynamic models is actually a big topic. Right? Really big books have been written and are still being written about hidden Markov models and Kalman filters and all that good stuff. And these books are great. I mean, it's all very justified because there are quite some computational issues when you want to do inference in dynamic models. But the issues are computational. So what I wanted to show in this class, that in principle, nothing changes. When in the framework that we treat here, right? You want to model a data set. And you build a model, a probabilistic model that tries to generate that data set, and then you solve your problem by inference. Whether it's learning the parameters or updating the parameters or predicting the future or classification or something, it's always just an inference problem. And that is no difference for dynamic models. That's no difference whether it's a static or dynamic model, it's just the same. The only difference is that we make different assumptions. In dynamic models, we make the assumption that not all data points are independent from each other, right? In time series or video, it's very common that the value of a pixel is related to the values of neighboring pixels, and also over time there is a relation. And as long as we try to capture that relation in some model, right? For instance, a transition model, as we do in time series, then everything works just as before. So you just build a model and you just write down your inference equations, and that's it. And for very particular models, very special models, if everything is linear and Gaussian, and you can solve that inference equation, and then you get an algorithm that's called the Kalman filter. But in a sense, that's sort of like an effect that you discover in the end, right? You don't set out, let's build a Kalman filter. You just build a model, and let's say you choose a linear Gaussian dynamic system, and so everything is now a big Gaussian, and you can solve your filtering problem analytically, and then the equations, they turn out to correspond exactly to the Kalman filter, and that's a filter that has been derived in a very different way, with innovation sequences and other kind of terminology in different fields. And but it can also be derived here just by using a Bayesian approach. And you can make your model much more complex, and very likely you cannot do not get analytical answers to your inference problems. Yeah, and then the big issues arrive, the computational issues. Perhaps you can use Laplace approximation, or you can use variational Bayes, and all that good stuff is described in the literature, and there's still ongoing literature on how to do this efficiently and robustly. And all that together makes up this big space of dynamic models in machine learning. But the main thing of this class is not to go into all the complications of the computational aspects, but to just show that really nothing changes. Probability theory is about logical inference, logical and not temporal, right? You can, if your probability, if you include a transition probability over time, well, then you do logical inference over time, and that's really all there is to this class. So with that, I would like to just pass it on to you. You can either say something in the chat or raise your hand, and I will try to answer your question. I don't see anything yet. I can be either very happy about that, or I've lost the whole class. Let me just ask a question. So the question is it indeed true that you have that everything is understood, that you particularly understand that when you go from a static model to a dynamic model, really the only thing you do is add some probabilistic relationship over time, right? So to be specific, let me just see if I can share my screen. All right, so there are various ways of doing it, but here's a particular way, right, where you say x of t is not independent of the other samples. No, it's actually related. Having knowledge of past samples improves my prediction of x of t. And here's the relationship, right? A linear relationship on the previous samples plus some Gaussian noise. And just like in the other models, we can add latent variables. And if we add latent variables, then we get something called a state space model, which is exactly the same model, state space models that you get in your control class and also in some communication classes. So it's all exactly the same thing. The most common assumption is a Markov assumption, which means that this gets added to it, right? I mean, up till now, we used to basically have x given z, the latent variables, times pz, but now we have that p of z is a function of previous states, right? So here's the time dependency. But aside from our model assumption, it's just a matter of inference, right? Use a very typical or very widely used model, a linear Gaussian dynamical systems. Everything is linear and Gaussian. In that case, you can derive the posterior for the state given the past observations. It's quite nasty to derive it because you have to use these Gaussian multiplication formulas. But in principle, it's straightforward, right? If you have this table lying next to you on your desk, it's pretty straightforward. And then you come up with these equations, and you can check that in the literature. This is just a Kalman filter, and the Kalman filter has also been derived in many other ways, but I've never seen it as simple and as quickly as through the Bayesian way. Usually, it takes 5-6 pages to go from let's say the model assumptions here to these Kalman equations, and this derivation is still doesn't look good, but it's very short. So that's one way of deriving a Kalman filter, but just saying, well, let's just do inference, right? And you can, of course, do anything else. You can say, oh, let's do the probability for x of t plus 1 given the past, and well, then you do prediction, but it's still just an inference problem, and everything is Gaussian, so you'll get an answer, right? Everything is solvable in these systems, and that's it. That's basically the whole class. I purposely did not make it very long and didn't go in all the difficult computational aspects when you introduce nonlinearities and all that stuff, because I want to make the point that we can use exactly the same methods and tools that we've used before. Well, now I introduced it twice, and I still don't see hands. Is it true that maybe you can just say that in the chat? That there are no questions. I see. Okay, Sweta, you have a question?
Yeah, so I just wanted to get some clarity on like what exactly we are trying to do. So I get that we have the concept of like time series involved, and so the identically independent and identically distributed data is no longer valid. And what is the role of ZT and XT? Is ZT the like what we would get by mathematical formula, and xt is what we actually observe, and that has some noise in our observation. Is that what it means?
Yeah, that's exactly correct. So we are in this class, we're just in the business of trying, we receive a data set and we try to build a model for it, right? Let me just, I'm going to show the screen again and just jump a little bit across the class, right? So we say, okay, we observe a data set, right, here, and we need to build a model for it. So as before, P of X, right, X superscript T, that's just, just a notational convenience or shorthand for the whole, basically the whole data set from 1 to 2. Now, we as engineers, we know this is a data set that comes from, let's say it's just a speech signal, all right? So then we say, well, these x1, x2, x3, they're not completely independent, right? I mean, there is a certain, if I receive a sample, then I want to, let's say we want to predict the future of speech signal, then it helps to know the past. So these samples are not independent. So the only thing that we do then in this class is, okay, let's try to capture that in a model, right? And there's different ways you can model it, but by far let's say the most popular way of modeling sequences is by state space models. And that means that, yeah, I have an observed data set, my sample. So this is my time sequence. And I have Z, and Z are now latent variables. And importantly, they're for each observation X of T, I get a new Z, so also a Z of T. They're not observed. And then maybe I should have written that as well here, comma theta, right? The parameters. And the only, I mean, both Z and theta are hidden, unobserved variables. You only observe the time series, X of T, the speech signal. And what this model will do, let's say, is the model P of X of T, comma ZT gamma. This would be a model that I can draw samples from, and then I get, basically, I can generate speech signals. Right? So how are speech signals caused? Well, it's, you can build your own model, you can have your own hypothesis, but one way would be, well, there is sort of like the shape of the mouth, right, and the throat and the tongue. They would be state variables. They change over time, and they're going to have some influence on the speech signal that you receive, right? You may not observe the location and the movement of the tongue, but if you want to know if you want to generate the future of a speech signal, it may be helpful to know that. So what we do here is just build a model. A generative model for a time series and we allow for latent states. Latent states are latent variables that change over time, and latent parameters, or latent variables that do not change over time, and we call them parameters. And aside from, so this is the most common model then, and then you need to make choices, right? You can say, okay, the X of T could be discrete data, or it can be continuous data. And the state space Z of T could be on a discrete alphabet, or it could be on a continuous alphabet. If it's on a discrete alphabet, we call this whole model a hidden Markov model. If it is on a continuous alphabet, we call it a dynamical system. It's just a label for the name of this model. Yeah, but the questions that we want to answer are always inference questions. And yeah, in principle, you can just write out by sum and product rule, what is the question that you want to answer? Estimate maybe the parameters, or make future predictions, or classify a time series. This is all fine. right? But it depends a bit on your what your goal is. So in a way, this class doesn't differ from the other classes. This is just you get a time series and you need to do something with it, maybe classify the speech, or you want to predict the future of the weather, and these are temperature signals. The way to go about it is always through a model. You build a model, and then you teach that model by giving it data. You update the parameters, and then you use the model to make the prediction, or to do the classification of the speech, or to do any task that you want. It's no different than the other class before. Is that sort of understood?
Yes. So I have a couple of follow-up questions.
Okay, go ahead.
So when we say initial state, so we mean like just before we start observing, what is the output that what we might potentially see if there is no noise, if there's no disruption. So that's why we have P of Z1, correct?
Yeah, I mean, there are two things I need to say about this. One is I go against my own notational convention here, right? The proper way of writing this, and I will update that, is P of Z given ZT minus 1 equals a Gaussian over ZT given the parameters, and the mean parameter is A ZT minus 1, and the variance is sigma Z. So also the P for Z1, I should have written here a Gaussian over Z1 given the parameters, the mean mu1 and the variance sigma 1. So this needs to be updated. But yeah, so this one here, let's say the middle one, is what's called the observation model. It says like, okay, what's the distribution for my observations if once I know the state at that particular time? And if I know my state, then, well, we say, okay, in this model, the observations is some kind of a linear combination of the states plus some noise, right? Because, yeah, and that noise that just serves to basically for our uncertainties, right? This may not be the perfect model for what's really going on in the world.
Right. Okay.
And the first one is then basically the temporal aspect, which says, okay, the P of Z's of T, so the Z of T's are not like independently drawn at every time. No, there's actually a relationship, right? Once when the temperature is 30 degrees yesterday, then it's probably not going to be -5 tomorrow, right? It's more likely that it's going to be between 25 and 35 the next day. So that you want to capture in this what's called a transition model. So P of ZT given the previous state, some relationship, some probabilistic relationship. Now, if I want to run this model, let's say I want to start at some point, let's say t equals 1 or t equals 2 or t equals 0, then I need to start out with c at t minus 1. Otherwise, I cannot run this model, and that's what. So this is the initial condition, the initial state, and we may not know that initial state. So again, here we say let's just assume it's some Gaussian, right? We have some uncertainty about where the model starts, but it starts in some state Z1, and then we can run it. Then we can produce from Z1. PZ, I should actually say it would be better to say PZ underscore T equals 1, which would be actually ZT0 then. So let's say we start at PZ0, some Gaussian, and then we can run the top equation to get a distribution over P Z1, and with that we can compute the probability for Px1 given Pz1, and so now we have a distribution for Px1, and then we continue. We say, well, given Z1, what's the probability distribution for Z2? And with that, we can compute the probability distribution for x2 and so forth. Right? You can also see it kind of in this vector graph. Basically, the generative model, it's here, right? You start in some state, and then you generate here x1, and then the state gets updated to z2, and you generate x2, and so forth. This is the generative model for observations x1 through x capital T.
Right, and could you briefly explain hidden Markov models? I did not get the state transition probability and that equation, the update equation.
Yeah, so generally, if you, let's say, yeah, if you are here, I'm going to build now a model, right, for my whole sequence, P of x1 through x capital T. And I'm going to break that down now in factors, and then I'm going to write down an equation for that factor, let's say a Gaussian or whatever. But you can't do this, right? This is what we used to do. We say, oh, it's just the product of the probability for the individual samples. But no, the individual samples now are a function of previous samples, right? So, but this decomposition, right? The probability for a whole sequence always decomposes into the probability for the first sample times the probability for the second sample given the past, times the probability for the third sample given the first and second sample, times the probability for the fourth sample given the first, second, and third sample, and so forth. This is just probability theory or the product rule. There's no, let's say, approximations here. This is always true. And then now we want to say, so we want to choose, for instance, Gaussians for this. The only thing is that these terms, P of x of t given x, x of the entire past, right? The number of variables in this probability distribution keeps growing over time. So we really need to limit that. We need to say, well, x of t at t is 1,000 doesn't depend on t1 and t2. It just depends on the last 5 or the last 6 samples, right? So then you get to an autoregressive model, right? So that limits the dependency of that sort of is a constraint on this one to make this all computationally doable. So we say, yeah, x of t is really just a function of the last k samples. Now we can do that even further. We can make the particularly in state space, it's useful to make the assumption that the state at a particular time is not just a function of all states from t is 1 to t minus 1. Now let's just assume that it is only a function of the previous state. So it's a very severe constraint. This constraint is called the first order Markov condition. It's a very useful constraint. In the exercises, the first exercises, we show that if you impose this constraint in your model, then basically given the present state, that the future, anything that you predict about the future is completely independent of the past. So you only need to remember present state. Right? This is what we prove here. It's a nasty proof. You don't have to know this proof for the exam, but we prove here that if we make this basically the first order Markov assumption, right? So we say, I have a time series. I'm not going to let x of n or c of n depend on all the samples in the past, but just on the previous one. Then, if I want to predict all samples given x of k, and all samples meaning excluding x of k, right? So from x of k, I want to predict both the future and the past. then that breaks down in predicting the future from xk and predicting the past from xk. So in words, if this Markov assumption holds, then given the present, the future is independent of the past. And that, I mean, that creates a tremendous amount of computational simplicity, because as you move forward in time, you don't need to remember the past. You only need to update your state, and you say, okay, whatever I want to predict about the future, I can do it with the information in the state. So we only update the state, and then we can do everything. That makes it computationally, a very lucrative model, and that's why it's so successful, the state space model, and that's why the first order Markov assumption is extremely widely used, because it's computationally very useful. That doesn't mean that every time series in nature works this way. It's just that these models, these Markov models, are usually good enough to accomplish your task. Right, so when I say they're good enough, I mean that the Bayesian evidence for that model is good enough to accomplish the task. It's sort of a good enough model, and it's computationally tractable. Right, you get, for instance, if we do it all in Gaussian, right? Then we get these this Kalman filter, and for the discrete time case, we get forward, they're called forward backward filters or Baum-Wells equations, but we get similar stuff as the Kalman filter. So really a compact algorithm, and so that's why it's a very useful assumption to make the state space to make the first order Markov assumption. You don't have to do that. It just turns out to be a useful assumption. Okay.
Yeah, so but my doubt is mainly with the discrete state variable model and under hidden Markov model.
Okay. So let's say here.
Yeah. Do not get how we are getting that equation on the that expression on the right hand side.
Yeah. So that's just it is a hard to interpret, but basically all I want to say is that. Okay, so you have here, we assume capital K states that the system can be in. So a discrete number, right? Let's say K is 6, so I have 6 states. CT can be one of 6 states. And what we will do is we will encode, as before, just think of them as clusters, right? We encode Z of T, one hot-coded latent variable. That means Z of T is a 6-dimensional vector, and it has all zeros except for one of the entries is a 1. And then we're interested that when I go, what is the probability distribution that I am at time t in the kth state? And we say, oh, well, the probability that I transition to the kth state from another state at t minus 1, namely state j, that's given by a sub jk, right? So it's just a number between 0 and 1. That is the probability that when I am at t minus 1 in state j, that is the probability that I transition to a new state k at t. And the way to write all that, let's say, I can write it this way, right? And this way is exactly the same formula, but now combine everything, right? And combine it, let's say, I don't say here ZTK equals 1, so I'm not saying anymore. So this is for all entries, and this is for all entries. So this is like the whole matrix here. You see all AJKs are here, and they are only selected. AJK is only selected if ZT minus 1 j equals 1 and ZTK equals 1. These are just like before. These are class selectors or cluster selectors, right? They're just the AJK is only selected if the, let's say, the what's in the exponent equals 1. you can really compare this to how we wrote the basically the categorical distribution. If you go back to the categorical distribution, this is basically a two-dimensional categorical distribution. There's nothing different really.
So then how do we pick which state it would be at time t? So after computing this probability, we observe and then get its distribution, because then for time t plus 1 we need to know what state it was in, whether it was what is the value of k, whether it was in the first state, second state.
Yeah.
So after computing this probability, how do we make that
okay, so let's say that we do that in the context of filtering, right? So let's say that over time you get x1 and then later you get x2 and later you get xt, right? So you start by saying, okay, I don't know, I mean, all this model does is basically update the states, right? I start with a probability distribution over the first state. I don't know which state. I mean it's I wrote down a Gaussian distribution or some other distribution, a categorical distribution. I say, okay, that's my knowledge at the beginning about the state. And then I make my first observation. Now, you can do it in different ways, but it's just inference. But in a vector graph, it's just passing messages. So you pass the message, and here I have an equality node. So here now we come, basically this observation updates our probability over Z1, right? So basically when we get an observation, we have some more knowledge about what Z1 really is, because I have, the initial P of Z1, but once I make an observation X1, then this distribution P of X1 given Z1 also provides some information about Z1. All right, this is, if you will, the likelihood function then for Z1, right? Because I'm going to fill in here the, let's say X1, and so this becomes a function now of Z1. It's a likelihood function for Z1. So I have a prior and a likelihood function. And in this equality node, you will multiply the two, you will do Bayes rule. And here in message 4, this is the posterior for Z1 given observation X1. We don't actually make a selection. We never say, okay, and now we declare that Z1 equals 3 or 4, right? We just are content with updating probabilities, because we still, after this observation, we may still not be sure what is really the state, but we can update our state of knowledge about the state space, and we get here in message 4 would be P of Z1 given X1. Then we go through this transition probability. We basically multiply with this transition PZ2 given Z1, and we integrate out Z1, and we get here, the probability for Z2, this is message 5, the probability for Z2 given observation X1. And we've integrated out now Z1. This is a hidden variable that we've integrated out. That happens just by message passing. You don't do that explicitly, right? You just pass messages in the toolbox. But message 5 is P of Z2 given X1. It's in a sense a prior for this state because I haven't observed X2 yet. But once I observe X2, then this message 6, once it passes through here and I integrate out over X2, I get a likelihood function for Z2. And this likelihood function, message 7, plus the prior Bayes rule delivers message 8. What is message 8? Is the probability for Z2 given X2 and given X1, and so on. And so I keep updating my knowledge about, let's say, I go through this recipe of creating a prior for ZK based on the past, and then multiplying that prior with a likelihood that comes from an observation, creating a posterior for zk, and then going through the transition model to create a prior again for zk minus 1, then a posterior for zk minus 1 through the likelihood, and so forth. Do you kind of see that? And that zk, let's say this probability distribution over z, yeah, z could be anything, right? It could, like in the speech, it could be the location of the tongue. Maybe that is what you're interested in. Or it could be the fundamental frequency of the, let's say, the pulses that your glottal, well, the glottal pulses, let's say, that comes out. Basically, the vibrating of your larynx leads to pulses in the signal, and it could be the frequency of those pulses. It could be anything. It's just some unobserved variable that you are where you're updating your knowledge about these variables based on the observations that you get. And I don't know what you're interested in, whether it's the position of the tongue or something else. But that's how that works.
Well, yeah. For the continuous case, it's clear, but for the discrete case, you need to know what is ZTK, right? So
for the discrete case, it would be the same thing. You would also, you only change, let's say, integrations to sums. So you would, you still get a probability, let's say, message 4 is a probability distribution over Z1 given X1. That's also the case for the discrete case. It would just be a categorical distribution, right? It would just be, oh, I have 0.3, let's say 3 states. 0.3 is the probability that it is in state 1, and 0.3 in state 2, and 0.4 in state 3. And then I go to a transition, and I integrate, and I sum out now over Z1, and I get a prior, again, a categorical distribution over Z2, and so forth. So it's the same recipe. It's just, so you never really make a hard decision on what the state is. You are content with updating your beliefs, your state of knowledge about what the states might be, because those causes, ZFT, are unobserved. You can't know for sure. But probability theory supports that you compute this in, let's say, the rational way, in the proper way.
Okay, so so I get that the probabilities. So I get what you mean by the categorical distribution. So we say that there is some confidence that it is probably in this state with certain probability. So then we do the state transition. We still we are having the powers, right? So and should they not? Isn't it one hot coded? So that is the place where I'm getting confused.
No, so this is really just a probabilistic system. So let's say message 5. Message 5 is some categorical distribution over Z2, and let's say it's a bit of a vague, sort of like almost a uniform distribution. If I have, let's say, 3 states, they're all about 1/3, these probabilities, right? And then you get a new observation, X2 comes in. But in our model, right, we have this, in our model, we have defined here a probability distribution, PXT. What is the probability distribution for X2? Once I know if the state ZT is given, Z2 is given, right? This relationship also can, I mean, you want to kind of invert that now, right? You want to say, well, Z2 is not given, X2 is given. And that turns this into a likelihood function for Z2. It provides information about Z2 if you know the observation X2. And that information you want to combine with this this prior information. It's just, and then here, yeah, you just do an update rule in a vector graph and you don't think about it. But internally, what will happen is message 8 is just a multiplication of 5 and 7, which means we're executing base rule. We just multiply two sources of information about what Z2 is, namely all the information we've collected from the past and the information of the most recent observation, and we want to combine that. But we never say at any point, I am sure that Z2 is in the third, let's say the third state or the fourth state. Yeah, unless the data says that, but otherwise we don't want to inject any other rules. So yeah, it remains a matter of just updating probabilities over states.
Okay, yeah, thanks. Thank you so much.
Sure. And the way you should think about it a bit is that if I keep updating probabilities over states, then basically what I'm saying is that if I, let's say that I would actually compute this whole thing, right? There's all these probabilities. So message 5, message 8, all these messages, right? And now I have basically a big probability distribution over all z's and over all x. Yeah. And I can say, okay, the x's are given. So let me just plug that in. So in that probability distribution. So now I see some probability distribution over all the z's. I can just draw samples from that distribution. And basically, that would say, what you're saying is, yeah, it could have been generated in this way, or it could have been generated in this way with a certain probability, or the same observation sequence could have been generated with several state sequences, right? If you make some observation sequence, not necessarily or almost never is there only one model that could have generated, or one state sequence that could have generated that observation sequence. There are lots of state sequences that could have generated that observation sequence, and they all have a certain probability. I'm not sure if I'm just making it more complex for you. If you don't get that, just forget about it. Are there any more questions? Do I see something in the chat? Not. Okay, so we are 45 minutes into it. Sveta, thank you very much for the questions. I really mean it, because it allowed me to to explain more in depth what we're doing here, and I'm sure it's also very, or hope it's also helpful for other people. So really appreciate your questions. Are there other questions? So if not, then I'm going to close or stop the recording right now. Let me just do that. Stop the recording.